Shine strong interaction program. So our main focus is to scan the phase diagram of strongly interacting matter. This is done via the 2D scan in collision energy and system size. So the collision energy for the SPS is between 5 and 17 GeV, and we collide various nuclei. The flagship goal of the experiment was to find the critical point. This turned out slightly slightly underwhelming. Still, the scan of this two-dimensional scan turned out quite interesting, and with this we uncovered quite an interesting region of various domains when you look at different collision energies and different sizes of the colliding nuclei. Some parts of what we've seen at lower energies are well described by the hadron resonance gas model. Some parts are well described when we assume that we have a QGP, and there is part which is nicely explained by the models involving string dynamics. So this is interesting, but this is not what I want to talk about today. So the main, I'm jumping straight to conclusions here. So the main measurement that we want to advertise is the asymmetry between the charged and neutral kaons. We have all the good reasons to expect that they will be that the yields will be the same. So the ratio of charged to neutral would be exactly 1, but it is not the case, and we measure significantly more charged kaons than the neutral kaons. So the first paper is the one describing the charged kaon results, and the second is for the neutral ones. So it translates to about 4 additional charged K mesons per central argon-scandium collisions when we extrapolate to the whole phase space. So this is indeed quite significant.
Can you remind me what argon and what the proton and neutron number of argon and scandium are?
So this is the atomic numbers is 40 and 45, and the number of protons is 18 and 21 respectively.
So this is already isospin-symmetric.
Yes, but we will talk about later how what is the expected.
Can you tell how many K plus versus K minus, or only the sum?
I don't remember, but if you look at the
screen, you can pitch the screen.
I can pitch the screen. Okay.
Yeah.
Okay.
And make it bigger or smaller. Yeah.
Okay, I better not touch. Anyway, so this is the normalized distribution. So if you integrate it, it goes a couple of tens, probably. No, the pions were a couple of tens, so this is something like 20, if I remember correctly. Yeah.
Can I just quickly ask? So on the right, you have the ratio, and you have an error bar, but you have PT dependence, right? But the number of PT points is a little bit scarce, maybe for K0 short. How did you get the smooth line? This is error propagation, I guess.
So if we fit the PT distributions with simple exponent function, which is obviously very simple and naive assumption that it will fit, but for the kaons by accident it fits because the various effects that.
Okay. So the bend there is just the fit parameter error propagated.
Yes,
okay.
Yes,
so exactly. You could, I guess, there are a few PT points where you could actually just put the raw data, right? Itself.
Yeah,
but it's consistent, right? I guess.
Yeah, that's
the errors.
That's right. So yeah, basically I could end at this point.
And then so here it's K0 short, right? And then do you have K0 long?
Yeah. So let me jump a couple of slides forward. Am I jumping or not? Oh, yeah, this is what I want to show. So we have K0 short and K0 and K0 bar. They are mixing to the eigenstates of K0 short and K0 long. So I touched again. And then K0 long, its lifetime is too large to be experimentally accessible, at least with such a short detector as the Na61 show. So we focus on the K0 short, and we say that the amount of K0 shorts is exactly the same as K0 long. And this, I think this is accurate, very accurate. That there is no problem with that. Yeah, so I will get back to this in a second. Right, so as I mentioned, I could end the talk at this point. I showed you the interesting result, but still I want to speak a little bit about all the interesting implications and maybe possible explanations of this effect. So I will start with explaining the background. So what are the symmetries that we expect? I will explore some ideas how to test this charge symmetry that we expect. I will explain how do we measure both charge and neutral kaons. I will then discuss the results and possible known effects and possible explanations of those. So we start with isospin. It goes back almost 100 years ago to Heisenberg and Wigner with introduction of the isotopic spin, which uses spin formalism very similar to like the electron spin, some additional degree of freedom, and we can, from the point of view of strong interactions, we can treat protons and neutrons as the manifestation of the same object, but with a different isospin, and then it's this kind of property can be assigned to both nuclei and hadrons. And yeah, so we see that the ratio of masses of those two objects is almost one, they're almost identical. So yeah, I believe that that was the original idea why those might be the same objects. So then we can talk about the isospin charge symmetries. So we have the charge symmetry transformation, which is a special kind of isospin transformation, and under this transformation we can transform proton into neutron and vice versa. And under this transformation, the strong interactions should behave the same. And we have one doublet, which is proton-neutron, but we could also form isospin doublets from K pluses, K0 bar, and K minus. And now we can wonder how does it translate into the QCD. So within the QCD, we can trace back this isospin symmetry to the light quarks. So under this charge transformation, we can switch U and D quarks, and as long as the masses of those quarks are equal, which is quite reasonable assumption considering that their mass difference is only about 2.5 MeV, comparing to the QCD energy scales, this is negligible. And so we have very known mesonic multiplets forming, nucleon doublet, pion triplet, kaon doublets, and we frequently talk about some reactions conserving isospin, for example, a collision of protons going into lambda K plus and proton. So it is very well known topic. And then we can try to think how to test the charge symmetry in production of charged and neutral kaons. So we have the charge symmetry transformation, and if we have a reaction of proton plus proton going into K plus and something, if we apply this charge transformation to this reaction, we have neutron plus neutron going to K0, and we can do the same with the K minus. But the right hand side of those equations are very difficult to measure. We cannot collide neutrons, so this is why we need to develop something different to test this charge symmetry. Yeah, maybe one word that those equations, they translate into the fact that if we measure the mean multiplicities of K pluses and K zeros, we can say the same multiplicities of K plus will be created in proton-proton collisions as K0 for neutron collisions. and same is true if we reverse it. So an idea is that we collide 50% of protons and 50% of neutrons. So then those two transformations will nicely add up, and we will get the mean multiplicities of K plus will be equal to mean multiplicities of K zeros. So we will have a charge transformation invariant final ensemble. So this is very simple setup of the experiment, and now we will try to think how to.
Excuse me?
Yes.
May I ask a question from here in Seattle? This is Jerry Miller.
Yes.
The isospin equality refers to particles of exactly the same momentum. So you're doing something that is going beyond isospin when you talk about the ensemble. In other words, protons and neutrons are related by isospin rotation only if they have exactly the same momentum and the same spin. And here for kaons, they have to have the same momentum to make a true isospin comparison.
Right. Yes, I'm not considering momentum in this.
Yeah, but if you compare particles of two different, you can compare a kaon, a K plus, and a K zero of different momentum, and the isospin is not relevant.
But I think this is integrated over momentum, right?
Yeah,
so the assumption is that distributions are the same.
Yeah, so it's something other than isospin.
Yeah, but on his first or whatever third slide where you saw the spectra, there you can compare them at the same momentum and they differ, right? I mean your money plot.
Yeah, but that was also K plus plus K minus.
Yeah, that's another question.
Yeah.
I would like to see K plus and K minus separately.
Well, this is of course doable, and then you don't have the K zero long as well. But okay, maybe so. This is just a simple setup of what we would like to do with the experiment. This is, as already said, integrated over momentum. So we only think about the mean multiplicities, and I am fully aware that I'm making a lot of shortcuts here. So this is just to simply sketch the situation. You are all much more proficient, so yeah, we can discuss later. But in general, the experiment here would be constructed in such a way that by construction, assuming we have the same number of protons and neutrons, by construction we will have a charge invariant initial system. Then we also have, well, this is the prediction of the experiment, that we will have the charge invariant final ensemble. So the tested assumption is that the interactions preserve the charge invariance. So we established on the previous slide that we expect that the mean multiplicities would be equal of those kaon isospin partners. So we construct the experimentally measurable ratio, RK we call it, written like this. So we sum the multiplicities of K pluses and K minuses. We divide by the 2 times the multiplicity of K0 short, assuming that it's a good approximation of the sum of the 2 K0 states, and it's supposed to be 1.
Excuse me.
Yes.
I want to ask a very simple question. So your test assumption says something about interaction. What you would obtain if there are no interaction? What is your baseline?
I'm not sure if I understand. I mean, we have So
you have some mechanism of interaction, right? You want to test your assumption that is the preservation of charge invariance, right? But the question is that with what you can compare, right? If there are no interaction, if there are no interaction at all, can you check it and see what you would obtain? Like the violation, for example.
No, I cannot think
maybe
of such a test. So we are testing the the strong interactions, and we are trying to see if in the strong interactions the charge invariance is preserved, right? So we have.
I should understand that you're testing the assumption about the preservation itself.
Yes, exactly.
So it might work or not work, and you cannot check, let's say, the opposite scenario.
Yeah, so you can. I mean, maybe I'm confused, but I don't think I understand. So if you have a situation where you can form the this initial system, which should be charge transformation invariant, right? If you transform, so maybe I have it on the one of the next slides. Let me see.
Actually, our baseline doesn't have interaction. It's ideal HRG.
So you answered my question now. So you do comparison, right?
Well, I think in what interactions.
So the baseline is not it's ideal HRG, but interactions here doesn't matter much.
In HRG.
Yeah, we try different interactions and ideal HRG.
I think I understood your answer. So then you compared it with the
Yeah, we compare it with ideal HRG.
That's all again.
Okay, so it seems I didn't fully understand the remark. Right.
So why should be K0 and K0 bar the same yield?
It's the sum.
No, it assumes that you K0 plus K0 bar is 2K0.
It's 2K0 short. We have the mixing of
I missed it. Yeah, got it. I missed. Wait a minute. But still, the K0 bar goes also to what? I'm rusty.
They both go to K0 short or K0 long with 50%. Right?
Yeah, but still, right? I mean, I have less. I mean, the K0 bar, because my medium is not has a finite chemical potential. It's not a C even. The K0 bar might be absorbed differently than the K0 because one has a strange quark and the other one has an anti-strange quark, and we know that the K plus and K minus in matter they behave differently, right? So,
and I think the reference is to hadrons after collisions. So mean numbers after collision of the sum is just 2 times K0 short. So it's all in the final state.
It's just that they don't see the K longs, that's all.
Yeah.
okay.
There are, where do the K stars come in? Do they, K to K pi, do they not affect this ratio at all?
They could, but we have quite a good control of those effects with Monte Carlo generators. So from the perspective of measurement, it is not an issue.
So with the K star, fit down is included in the measurement, right?
Yes.
So it's all after all strong decays.
Yes. Absolutely. So the results of each NA61 measurement is after the corrections for every strong decay, but also those weak decays that are still counting, right? So we try to account for everything that there is, as long as the model assumptions are correct, as we have good input to the models, but we also test this. We can assign uncertainty to this, this is included in the systematic uncertainty that we have.
What about associated production?
Yes, so that's an idea that is not very much explored because it's difficult. But you can try to run models. I think it might be easier to think about it if I advance with the presentation and I show you the comparison to the ERQMD and hadron resonance gas, and then you will know what exactly is in there, and it will be easier to think about it. Right. So maybe I will just mention that this kind of experiment we tested with the argon-scandium collisions, which are not exactly symmetric, but it's an effect that we can try to account for or try to estimate what would be the effect of this asymmetry. So we did this measurement in 2015, approximately, and then the second, more appropriate test are the collisions of pi plus at carbon-12 and pi minus at carbon-12. So then, if you have both, then each of this, when you have those two reactions and you consider them together, then the ensemble of pi plus, pi minus plus carbon, does not change under the charge transformation. So this should be the better version of the test that we proposed. And we already gathered the data in 2024. It should be, in a couple of years we will have. No, I'm joking right now. The analysis goes faster.
Don't give oxygen.
What is the energy of your pions?
I don't remember the exact numbers. I have it on one of the last slides.
I don't even know. Is it hundreds of GeV or?
Yeah, this is order of GeV. Those are SPS energies.
Okay.
Yeah.
So don't you have oxygen in your ensemble of events or measurements?
This is planned, but not yet done.
Oh, not done. Okay.
And this the pion carbon was very easy to get because we had already planned some test beams, and it was very very quick to do. And accidentally, pion carbon interactions are studied also in NA61 for the purpose of baseline for cosmic ray studies. So we already had some previous results that showed that this effect is present as well. Right, so now a little bit about the measurement. So this is the NA61 shine setup. So we have 4 large volume time projection chambers. In those time projection chambers, we record the points where traversing particle ionizes the gas. It produces something which we call cluster. Then the clusters are combined into tracks, and the track segments are combined into vertex tracks. So vertex track is assigned to the primary vertex where it originates from. We assign a momentum at vertex. We can determine its mass via the EDX and TOF measurements, and this is the input for our charged kaon analysis. And for the K0 short, we are using the decays of K0 to a pair of charged pions, and this is a slightly different analysis. So yeah, I've seen it before. So we are interested in these two. As I mentioned, K0 long are out of reach because they spend too much time before they decay, and of course there are other isospin partners that would be interesting to measure, but this is for future. For now, this is what we have. We look at kaons.
It's the whole.
No, this is the whole. This is the Higgs at SPS would be something amazing, right? Yeah. Right. So this is a detector setup. I don't want to spend time here. One thing maybe to ensure you about the trustworthiness of the experimental results. So we have a couple of PID methods that we can use for the identification of the identified hadrons. So each of them has different acceptance region, but we have overlapping parts, and this way we can verify. And actually, nice thing is that of course it takes a long time, but it's for the best, I guess. Each analysis is done by a different person, so then they don't have even common code base. So we really do verify each other and try to minimize a systematic uncertainty, which is very frequently calculated, which comes from the human error. So that's I think this might be underappreciated in general, and we try to minimize. Yeah.
So how come you're showing full DEDX coverage from, okay, it's PT. You don't have issues with the pions and kaons and other bands crossing?
We have, but the experiment is designed in such a way that where there is a crossing, we have another measurement method that covers you there, and you can stitch the two methods, and it's working quite nicely. Important thing compared to collider experiments is that we go actually down to PT equals 0. So this is something that you cannot get from colliders, and this is actually to 0, not like 0.1, but like 0.
I'm curious, so what does it mean here in this case PT equals 0? Like, how you made these measurements, just from my understanding?
So it's a fixed target experiment, right? So you have the PZ, so you have some track, and it is bent in the magnetic field, so it actually enters the detector. This is not possible with the collider experiments because tracks of PT0 would just go through the beam pipe, basically. Right? So this is. That makes sense? Right, so those are our PID methods, and you mentioned the crossing between kaons and protons, pions. So yeah, this is a problematic region, and those plots look very different than what you might see in ALICE, because of in ALICE everything is shifted towards lower P, right? Because you are actually looking at PT, and here you have everything boosted along the horizontal axis. So we rely heavily on this plateau region, but we can make a measurement there, no problem. Okay, and then we also have mass. So the mass measurement gives us some nice coverage in this region where it would be problematic for just the EDX, and this plot illustrates it nicely. So here we have a DDX, and here we have a kaon peak, the green one, hidden behind the proton peak. So it would not be possible to do it with just the DDX, but if you add mass to this measurement, you have nice island here, which is very easily identifiable. So yeah, we've got a great separation. And then when we go into the plateau region, we can make reliable fits to the DDX distributions, and we get a good results on the K plus, K minus, although admittedly this is difficult to get it right. And then we obtain the results. We scan a couple of collision energies, and we measure various charged hadrons. We construct PT distributions out of those YPT distributions, and rapidity distributions as well. In some cases, the PT distributions need to be extrapolated. In case of kaons, this is relatively simple. You are not making huge error if you just consider them to be exponent-like. And when it comes to rapidity distributions, you get also quite a good fit with simple double Gaussian. So yeah, in general, this is quite robust and gives you good enough measurements and uncertainties. Right. And with the K0 short, this, as I mentioned, this analysis is much different. So you have the K0s decaying to pi plus and pi minus, and then you look for displaced vertices in the detector from which two charged tracks are outgoing. You take all of those charged tracks and you construct invariant mass distribution out of it, and you look for the peak. So the branching ratio is almost 70%. So yes, statistically, it's quite favorable. So I'm coming back to the plot that I showed in the beginning. Hopefully now it makes more impact, and you can trust the results more, I would say. So we can try to plot this RK on just like it is. And interesting thing is that we should look at other data, what other experiments measured. So we have older NA49 results, which are surprisingly close, but with larger uncertainties. We have some more recent measurements from Hades and Star, which also show everything is above 1. And we have series, some very old NE35 measurements. The problem here is that the K pluses are also identified via decay vertex, and it substantially reduces available statistics. So that's maybe a different kind of measurement. But we also have ALICE, and at LHC, this ratio is consistent with 1, but it's also consistent due to large uncertainties with any value reasonably close to 1, but large. And then, as I mentioned, I will show you also the comparison with the hadron resonance gas and URQMD. And in those analyses, you can actually include the asymmetry Q P divided by V, right? So you can account for the fact that you have more neutrons than protons, and those do agree to a good degree, and we don't have such large enhancements. So the part over here, this is actually coming from the from not exact isospin symmetry in the colliding nuclei, but when we go to higher energies, this no longer makes such a difference, and it goes above 1 due to different masses of quarks or the kaons, right? Because
do these calculations include electromagnetic effects of the charged nuclei?
No, as far as I know, they don't.
Because those explicitly break isospin, and you have Z is what, 18 or something like that.
Yeah.
Z can be pretty big, so Z alpha is not so small.
Yeah, this needs to be considered, but also maybe one important remark I can talk already here about it is that if there was some effect proportional to the charge of colliding nuclei, you would see dependence on the Z square somewhere, and we don't see any dependence like that, right? Because you have two highly charged nuclei, right? And if you don't see any dependence on the Z square, then it's a hint that this kind of global effect might not be present.
I don't know. It may go like Z.
Yeah, but you have K plus K minus, so to leading order the Coulomb goes out, and down there you have K0, right?
Right.
Yeah. Okay.
They just asked for the previous slide.
Yeah, sure.
Well, it's also.
But is there any simple reason why the error from an A61 is smaller than any other experiment? Like, was it more deeper analysis or better detection, or so? What is it? What's driving this?
I should mention probably that several PhDs were significantly delayed because of this discrepancy. So that's we really worked hard on making a correct calculation of the systematic uncertainties. So I think the most direct comparison is to the NA49, and yeah, we made some experimental improvements. We installed the helium beam pipe and so on, so we got better readout and things like that. We improved the analysis methods somewhat, so we were able to reach extended parts of acceptance, for example, and then we also gathered more statistics. I mean, of course, statistics is negligible here, but when it comes to systematic effects, I'm quite comfortable that this is the...
Okay, I see.
So these error bars are almost entirely systematic?
Yeah, absolutely.
To what extent, and I realize it's a hard question, to what extent are those correlated between experiments?
That's an insanely difficult question, and we tried to think of because if there is a common systematic that would shift this somewhere, you could think of, for example, like you correct for the decay length of the K0 short, right? And if everyone does it wrong, then obviously you would shift every single point somehow. But we tried calculating the expected effect derived from the uncertainty that we have on those quantities, and they were nothing close to 20%. We might get, I don't know, 0.3% out of those kind of effects, but nothing really significant that would affect all of those experiments at once, because each one has.
Can I also ask?
Yeah.
To what extent the extrapolation to PT equals 0? You said you can actually measure PT equals 0, so that is not the issue for you, right? But in collider, usually that's the main source of uncertainty, or is it not?
Yes. So this is why the Alice error bars are so large, right?
Okay, and then related to that, you showed in one of the earlier slides this nice PT-dependent ratio. Is the version of that plot available for those other experiments where maybe this issue is extrapolating to PT0 could be taken out?
We looked at those, but we never made nicely browsable compilation of those results, right?
Because I think at PT differential should have much smaller error in Alice and probably in star. And there you can probably see if there is that effect, because it's supposed to be also at fixed PT there, right?
Right. Yeah, of course. So it's interesting to see. We try to gather on this plot as much as possible that we could understand what's being plotted there, what's being calculated there. And the details are always difficult to account for.
Do you know what is star isobar collision data?
Sorry?
Star isobar collision. Same recording.
Did they publish the yields?
I don't know.
I don't think they did.
There is one interesting new measurement, but I will talk about this towards the end of the presentation.
Can I ask you a question?
Yes.
Why the difference HRG and LR cumulative is different? Those two lines.
Oh, this is beyond my knowledge to try to explain.
It
Well,
is
they're
different
using
because phi meson is different in HRG. The decays to charged neutral kaons are different in HRG, but UQMD doesn't take it into account. That's why it goes to unity.
And it's a very different model as well, right? Right. So from what we've seen, it would seem that this tested assumption is being violated. We measured this RK to be different than 1, and this we'll call the charge symmetry breaking. And now I will go through a couple of effects that you already asked about, which are known effects contributing to this symmetry breaking in the kaon production. So the first one is the mass effect within the strong interactions. So we have different quark masses, and as a consequence, we also have different masses of the kaons, and this indeed brings the ratio up but only by about 2%. This was the estimation. But we also have already mentioned the phi decays, which also affect the kaon masses. They also affect the branching ratios because the phi 0 is right on the border of threshold of the K plus K minus production, and it's actually quite a significant effect, 1.45 if you compare the ratios. But considering how low the feed down to the kaons is, it contributes only about 1% at worst. One could also speak about A0 and F0 resonances, but those effects are even smaller.
So this effect should depend on the energy. Higher energy, the fraction should be higher.
Yes, and I think, if I'm not mistaken, this is what you this contributes to what you see here, that it's above 1. But yeah.
Why then the last point is the whole one?
Well, the error bar is pretty big.
This is measurement. So this is Alice measurement. So there's huge uncertainty, but the black point is there on the line. So
I didn't see it because of my visions.
Okay. Right. So we went through this slide, and Yeah, this is another version of the same plot that I showed before, but now this is to address the effects of the mass and the fact that the z is smaller than n effects, and they are included in those hadron resonance gas model and also the URQMD. And still, we see that if we take the average of all the experimental data that we have, we are on the border of 5 sigma with this. But interestingly, we have chi-square only about 0.3. So this suggests either what we discussed before, that experiments might be correlated, or that the uncertainties are actually overestimated, which could also be true because people usually tend to be conservative with the estimation of the uncertainties. So there might be some human bias here, but this is beyond what we can.
Would that decrease 4.7 if, for instance, they were correlated?
That would decrease the C.
Okay.
But an A61 point was moving down during the course of the project. So at first it was more than 5 sigma.
At first it was more than 5 sigma, the single measurement, and then the human error kicked in. So this is why we really spent a lot of time trying to get rid of every inaccuracy.
But when will be this 40A GV point available? The new A61 point?
I'm not sure. As I remember, this is already quite advanced, but those things, it takes time before it goes through the calibration review and later. But I have
some result bring it above 5 sigma again.
Yeah.
Preliminary.
Yeah. Interesting. And I think we might get those results from pion carbon scattering pretty soon as well. I mean, people are determined to really do this quickly. Right. So then we go to uncertainties due to weak decays, because weak interaction does not obey this kind of charge symmetry. And charged and neutral kaons have different mean lifetimes. And as I mentioned before, the results are already corrected for this effect. But of course, the correction themselves have some uncertainties. So if you consider this uncertainty and you try to move up and down with this uncertainty, you only get about 0.1% out of it. So this cannot be a significant effect. And then we also go into electromagnetic processes, which also do not obey the charge symmetry, obviously, because we either have charge or not. So if we were talking about the hadron electromagnetic decays, then those are suppressed by factor alpha. And I already mentioned that if we were thinking about any electromagnetic processes that would involve total electric charge of the nuclei, we would expect to see something proportional to the z square, also alpha square, so heavily suppressed, but still there might be some effect, but we haven't observed anything like that in the data. But then again, there is a question if UU bar and DD bar creation in strong processes, it might be affected by different field strengths. It might turn out that there are large QED corrections to QQ bar pair creation, but there are no calculations of this effect available. So yeah, it would be interesting avenue to explore. Yes, and now the question is if those charge symmetry breaking, if it's specific to nuclei collisions, or is it general property of the interactions? So we will have an answer hopefully soon from the carbon-carbon collisions. Those will be at 158 GeV over C. So there was a question earlier. So this is about 17 GeV collision energy. I don't. Right. So as I mentioned, those data are already recorded. The pion carbon scattering, 30 million events each. So as before, the statistics will not be an issue. We will have a very nice, good quality measurement Now it only depends on the available manpower when we'll be able to complete it. So there are two interesting papers that are on arXiv, but probably soon to be published. One is, as I understand, it's an update to RQMD, that this effect is explained through asymmetric production of quark pairs in the fragmentation of the color field. So if they increase the probability of new quark being created by a factor 3, then they fit to the E plus E minus data, and this is the data that they do the fit. So those are some new measurements from the BESS3 program. So this is electron-positron annihilation at energies significantly lower than what we explore here with nucleon. But interestingly, they also observed the K plus versus K0 short asymmetry, but they didn't observe similar with the charged pions and neutron pions. So this is interesting, but in the paper they say that those two are both consistent with isospin-symmetry in the Parton fragmentation process, which I believe tries to explain the in the same way both the our AA results and this electron-positron annihilation. But I admit that I only discovered those papers recently. I didn't even have time to really go through it. Right, so to sum up, we've seen this larger than one ratio of charged to neutral kaons in argon-scandium collisions. This would be the first experimental evidence of large charge symmetry working in kaon production. If you account for all the existing measurements, it cannot be explained by known processes, and we will have interesting data soon that will be able to answer some of the remaining questions. Right. So this time, thank you for your attention. Seriously.
I have a semantic comment, meaning ignore it, and then a question that may be totally irrelevant. So you go back one slide. In the semantic comment, I believe the middle bullet point is more correct to say it's not consistent with how we understand how to implement isospin violations, because you certainly wouldn't claim you found evidence of new physics, right?
Absolutely.
So presumably it's just our lack of understanding of how to.
No, you're right.
And so the question that's maybe irrelevant, which is why I was asking about K plus versus K minus, is as Volker pointed out, there's an asymmetry in the matter coming into the collision. And so I was wondering if you could count K plus versus K minus. Like the K plus is going to be produced with an extra up quark, and the K minus with an extra down quark. So some difference in the K plus, K minus production will give you some feeling for how much of the excess of K plus over K minus, whatever, is induced by the medium. And I missed if you talked about that.
So,
and how much will it even affect your anticipated production? Because the K0 and K0 bar are only from down and anti-down. But presumably, in principle, you can do the same thing with K0 and K0, but you can't actually separate K0 and K0 bar as experimental, right? So K plus, K minus might give you a sense of how much.
Right. So this. This is what we have, the spectrum in rapidity and spectrum in PT. And
so blue is K minus?
Yes. And
K minus is from D valence. I mean, you'd expect some excess of K minus from valence D quarks, right? And K plus from valence D quarks.
If you have more D quarks in the initial state.
If you have a system with more neutrons, you have more down quarks.
K minus is the U of S bar.
No, wait. K plus is S bar U, right?
Yes. K plus.
So there's
K minus is it's the opposite, right?
K plus is S bar U.
Yes.
K minus is U bar S.
No, K minus. Yeah.
K plus
Oh.
is S.
So you have to compare K0.
Sorry, I goofed that up. Sorry.
Wait. I'm pretty sure K plus has anti-strange.
No, wait.
It does.
No, my point is K minus can only come from a C, right? Because it's U bar.
Well, it's associate production, that's where it comes from, right?
Yeah.
Well, but whereas the K pluses will have
That's
some
true.
excess because of valence.
Yes.
Quarks. Okay, so maybe what I want to do needs both K plus minus and K0 minus separation.
Right. So, I mean, K plus, I think your plots are mislabeled. Usually you have more K pluses than K minuses, right? But
This is true. This is K pluses in red.
But on the top, if I look at the spectrum, one goes to 14, the other one goes to 20. So maybe
20. You're right.
They are mixed up.
I'm sorry. Yes.
Oh, okay, so then I guess the only way to feel the medium is to look at oxygen versus asymmetric systems. Okay.
Yeah, and oxygen might happen for NH61. I'm not sure.
So I think Jerry maybe have the same comment that what I want to say. Jerry, please go ahead.
Thanks. I want to come back to what I said in the beginning.
Yeah.
Isospin comparison is for particles of the same kinematics exactly.
Yes.
So you have to look at a K plus of some momentum and a K0 of the same momentum. So on this picture that's up here, there's 21 that you have, which is now. So this is only PT, but the longitudinal momentum could be different. Also,
that shows up in the rapidity, though.
Sorry, that shows up in the rapidity. And where is the?
This is mid-rapidity on the right?
Yes. This is
Yeah, but you have to look at the same rapidity and the same PT. That may be difficult, but that's the definition of chart symmetry.
So I think the right plot does what you.
The right plot shows PT, the left plot shows Y, and you have to compare.
The PT distribution is at mid-rapidity, so we integrate in a pretty narrow region of rapidity from minus 0.2 to 0.2. Well, we can discuss if it's narrow or not, but
yes. So the right plot is Y less than 0.02 or something. The right plot has rapidity cut, right?
Yes.
Okay, it's not integrated.
Look at that. Oh, yeah. That's already a difference.
Yeah.
Yes, I haven't included this information on the slide. Sorry for that. I must have omitted it. Yeah.
Anyway, also, I don't think the electromagnetic effects cancel. If you combine it with the kinematics, the K pluses are repulsed by the Coulomb field and the K minuses are attracted. And it's not only Coulomb, but these energies, it's likely to be magnetic as well. So the trajectories of the particles going out are different due to these electromagnetic effects.
So there is a group in Kraków interested in the electromagnetic effects, and they paid close attention to pi pluses and pi minuses. And the effects are there, you can see it, but you need to go to the peripheral collisions, and you need to look at the edges of the acceptance. So very, very low PT or actually very high PT and rapidity.
Okay.
So I can tell that about pions. We never looked at kaons in this much detail, but probably we will at some point.
So the proton-neutron ratio should be much better for this. Is it feasible to measure it? Because it's much more clean and less sensitive to known
oxygen. Or what do you mean?
No, I mean proton to neutron ratio instead of a kaon ratio.
But it's very difficult to measure neutrons. I mean, we have the calorimeter, but I'm not sure if that's feasible, to be honest. It has pretty good resolution, but no, I'm not sure.
There would be a problem with, I mean, there's neutrons that come out as single neutron, but there's also fragments, you know, neutron and a deuteron or neutron and an alpha.
Well, okay, the actual problem is that you can only measure the neutrons that survived from the projectile, and you have no information about the spectator. So I think that's the largest problem.
Yeah, it might be just some nuclear physics effects, right? Your neutron and proton distribute differently in the nucleus.
Mm-hmm.
And when collision, it's not guaranteed. I mean, of course, ideally, you just do the proton, neutron, right? I remember maybe 10 years or 15 years ago, there's a Formula-V experiment. They measured Upsilon. There's no isospin break-in. So they use the proton and the deuteron. So that's give you the same.
Can you do deuteron?
No, I think they have proton on the deuteron and proton. So yeah. I mean, it's good. I mean, another thing, maybe just follow what Jerry is just saying, that if you have to find a fundamental process which give you the same momentum for the initial and the final. I mean, just look back what people discover CP variation, right? If you claim something, you have to be very careful. I mean, of course, everything related to nuclear physics is so dirty, so you can claim anything. So maybe it's fun.
Yeah.
But this still doesn't explain the observation.
What do you mean? You compare URQMD?
Well, I mean, so we saw one is the hadron resonance gas, and I mean.
Yes, you compare to your model.
Well, you have an explanation for this difference?
No, I don't, because you don't know the nuclear physics. I don't have to, because it's so complicated, right? I mean, how you can make sure that you can describe all the nuclear interaction, right?
Yeah.
Yeah, that's the difficult part.
That's right. And in fact, it's not only the kaons that have to have the same kinematics, it's everything.
So how does your pi plus pi minus ratio look like? Is that closer to 1, or?
This is more difficult to
measurement
to measure because
you have the problem with the protons and the pions and stuff like that.
Yes, so you cannot extrapolate effectively towards lower PTs because pion PT distribution gets complicated at low PT because of all the decay products. You could probably do it, but it's a significant effort. So we never done it yet, the coverage is just not optimal. But this is something that we would be interested in seeing. But we can't really access the pi zero because we don't measure photons, and it's
But this ratio is not 1 because of even in the models because of initial asymmetry.
Yeah, but I mean that you can also compare with the model and see whether it's off or not, right? I mean,
there are more pi minuses usually.
Yes,
pi pluses because of the electromagnetic.
No, but
charge
you bring in more neutrons, right?
Yeah, you bring more DT quarks.
Right. The initial state has negative isospin, right? I3 from the neutrons.
Yes, you are right, but then I seem to recall that we had more. But okay, maybe I'm mistaken.
So net charge is positive.
So for pi, you just need to compare pi plus pi minus. You don't need pi zero, right? Because that's y is u, y is d. So
Yeah, yes.
should be. I mean, another thing you mentioned about the pi plus parameter carbon, you just measure the total perception. That's to tell you actually that's also isospin, right?
Yeah,
because the pi plus, pi minus.
But total cross sections were already measured, right?
Okay.
And they are consistent with isospin-symmetry.
Okay.
So that's another story, I guess.
Oh, and that's it. I almost forgot. So I want to ask it. How about lambda or something?
Yeah, this is obviously on to-do list. And if we are speaking about the S quarks, we should probably always speak about kaons and lambdas together because of the associated production and things like that. But those, those unfortunately take a lot of time.
Take a long time. Yeah. I think lambda is more convincing. I don't know.
You want to get past lambda?
Lambda bar.
Well, but this is party A and party B, the size has been 0. So I'm not so sure.
Lambda and lambda 0, lambda bar 0. You know, it's
Lambda is only 1, the size has been 0. You need to measure the sigmas, which is impossible to do as far as I understand.
Lewicki did that.
Yeah, well,
Very, very hard.
very hard, but
Okay.
let's call it very hard. So you,
Yeah, but centrality, except for central.
So for those intermediate size nuclei, we mostly had central triggers, so we can go outside the head-on centrality to like maybe 20% off, but not very far. We have some dedicated datasets, LED datasets for peripheral collisions, so we might be able to use it.
The trigger is based on number of spectator neutrons. Okay.
Both protons and neutrons, spectators, number of spectators.
So data in proton-proton collisions.
Yes, we have measured proton-proton collisions, but there is no such effect in proton-proton collisions.
So it's consistent with.
Yes.
So back to the nuclear physics. So suppose you have neutron spin, right? So the proton and neutron are not really distributed uniformly inside the nucleus. So in the sense that your kind of surface effect was
more neutrons, but I thought about this, but that means you remove some neutrons, so it goes actually in the
opposite direction. I always thought about that. Yeah, I was thinking about that.
It makes it more isospin-symmetric if I.
But now it's really nuclear physics. So suppose so then just run this through like this. So that but the central, suppose you have more proton in the central, but this is soft particle. So you may have more shattering contribution. So in this sense, you have effectively less proton-proton scattering. Is that possible? I don't know. Yeah.
It's tricky, right? But the trivial effect goes in the wrong direction.
Yeah, the trivial effect goes wrong direction. I agree.
Do you have isopath? You have isopath style.
Yeah, that's right. With that, one can actually, I mean, maybe Star will do. I don't know, start digging into this. Well, you are a Star.
Not for a long time.
Oh, really? I don't know. We have no Star here. All right.
It's interesting physics.
Your knowledge.
Oh,
I will check.
okay. All right. I think we should end this.